at 8:30, so I'm just going to start now. So good evening, everyone, and thank you for joining our Youth AI talk today. So last talk, we had Professor Peter Stone from UT Austin talk about autonomous agents and discuss his work in robotic soccer, as well as with AI and his future direction. And you can watch that on our YouTube channel. And next, I would just like to introduce some of our following talks. So 2 weeks from now, on October 4th, we will have Fiona McAvoy as our speaker. She will present some of the ethical concerns surrounding emerging tech, including bias, surveillance, and AI-driven deception. She's an AI ethics writer, researcher, speaker, and thought leader based in San Francisco, California. And she was named one of the 30 women influencing AI in San Francisco by Rework and one of 100 Brilliant Women in AI Ethics 2020 and 2019 by Lighthouse 3. She's also regularly asked to present her ideas to AI conferences in the US and internationally. On October 18th, Dr. Mark Esposito will discuss the implications of AI for society and the future of work. So Dr. Esposito is a business professor, best-selling author, entrepreneur, and senior advisor to governments, as well as the World Economic Forum. And finally, on October 31st, Professor Moshe Varde will discuss the interrelationship between humans, machines, and work. Professor Varde is a renowned mathematician and computer scientist. He's the top expert in automated reasoning, which is a branch of artificial intelligence. And he is the professor of computer science at Rice University, where he leads the Technology, Culture, and Society Initiative. Professor Varde is a member of the National Academy of Engineering, the National Academy of Sciences, the American Academy of Arts and Sciences, and the Academia Europae. He holds honorary degrees from 8 universities. So before I introduce Professor Huang, I'd like to first briefly go over the logistics of today's talk. So due to the fact that we have both viewers in the Zoom meeting as well as on YouTube, we'll be doing Q&A through a platform called Slido. So you can go to the following link or enter the event code 15062. Feel free to submit questions throughout the talk, and we'll have some time for Professor Huang to answer these questions at the end. So now I would like to hand it over to Professor Huang.
Unmute and share my screen. Can you see my screen? Can you hear me?
Yeah,
yes.
It looks good.
Okay, so thanks for Jeffrey for the introduction. Today I'm going to talk a little bit about my research. In particular, I want to introduce the research field I'm working on. So the title of my talk is called The Interplay Between Geometry Processing and AI in the Modern Era. So I will introduce the field called geometry processing with a bunch of AI applications and so on, okay? So I want to begin with, so this talk, so there's no mathematical equation or figures or some of the videos. I think this should be accessible to all of you, okay? So I want to begin with a story, personal story. The story is really about a city in Turkey called Ephesus. The city was over 5,000 years ago and was destructed. And these two photographs captures how it looked like about 100 years ago, okay? Over the years, people try to reconstruct the city, and this two figures showed a landmark building on that side called the library, which was reconstructed in the 70s, and this site attracts more than 3 million people, okay? 3 million people per year, okay? So back in 2007, I was involved in a project where the goal was to reconstruct a monument called Octagon. So the location of this monument was roughly located here in the pointing in the red arrow here. And So I involved the team, and basically this monument was destructed into many fragments. Okay, and it showed here. And the challenge was those fragments were very big, right? For example, if we really want to reconstruct a building by hand, this turns out to be almost impossible, right? Even moving a single fragment requires a very powerful machine. So how to do this? So we use the technology called 3D depth sensing, right? So we use the depth sensor. I will introduce the machinery of 3D sensor in a moment. But we use those 3D sensors, we digitize those fragments, right? So those big storms in computers, right? So those are the digital copy of those monuments. Then with these digital copies, we can apply geometry processing techniques to match them, right? AI machine learning to match them, to assemble them, and that turns out this was the very nice way to solve this problem. And this photograph showed a potential physical restoration of the monument, right? It was caught because of financial crisis back in 2009. I think this is still in the planning. Okay. So this is just a simple example of the field that called geometry processing I'm working in. So in fact that all the physical objects in our physical world, like the molecules to the things we eat, used to large scale objects such as buildings, can be exactly captured used as three-dimensional models. So as you see in this talk, the field of the applications of geometry processing is quite broad, right? We'll show diverse applications. So I want to organize my talk by recognizing the so-called the geometry processing pipeline, which lays the skeleton of this field. Okay, so what we have is that we start from the physical world. We use digital acquisition devices and softwares to reconstruct those physical objects into the virtual world, right? The three-dimensional models. Then what we do is that we do a lot of processing. For example, we want to process the 3D models. We want to parameterize them. We want to understand them, right? So that is so-called analysis, which I will talk about. Then once we understand 3D model, we want to generate new models, right? So that is called modeling synthesis. Once we have new models, finally, we want to go back to the physical world, right? We want to use the so-called 3D printing techniques, right, to generate new physical objects for different applications, right? So this is called the geometry processing pipeline, right? So once again, we are going from the virtual world to the physical world to the virtual world, then we go back to the physical world. So I want to start with talk a little bit about basically 3 parts, right? One is reconstruction, another is processing, in particular analysis of 3D models. Then I will talk about 3D printing briefly, okay? So let's start with reconstruction. If we put this reconstruction in the big picture called the visual recording, right? So we can think about, so this field is about 200 years old, right? So do any of you know when the first image? So when was the first image captured, right? So I can tell you that this is what was about 200 years ago, called Windows at No Grass, right? We found this. How about the first movie? Any of you know? In 1878, right? It's called The Horse in Motion. Right, so those are not really digital, right? They're this kind of like visual copies of the physical environment. But how about the first digital image, right? So this was in 1957, right? It's called the first digital image. Then how about the computer model? Any of you know what about the 3D model? Okay, so this was about 50 years ago, right? So this is a video, right? It's produced in Pixar, the first 3D model, right? It's basically a 3-dimensional copy of a physical hand. Okay, the first 3D rendered movie less than 50 years ago, right? But then you look at the basic acquisition device, the technology is very rudimentary. Okay, so what they did, right? So they they draw the polygon on the hand, right? They place the vertices, right? So then then what they do is that they record how the vertices should be connected, right? They mark all the vertices, all the edges, and then they use the so-called contact sensor, right? Contact sensor to record the location, the 3D locations of the vertices. And in the end, we have a 3D model, okay? So that was 50 years ago. So that was 50 years ago. And it turns out that we have made a lot of progress from the first model, 3D model. Okay, so modern reconstruction pipeline, of course, we are not using this kind of contact sensor to record the 3D shape. Okay, so what we usually use is so-called digital acquisition devices. There's just a very broad range of 3D digital acquisition devices, right? So those digital acquisition devices will turn the 3D model into the so-called depth scans, right? So for each view, we have a depth scan of the 3D model. Then what we do is that we apply some so-called registration technique, right? So we align the depth scans into a 3D model, right? So this is called a point cloud. Then we do reconstruction. Okay, so this is the modern reconstruction pipeline. So let me talk a little bit about this pipeline in more details, right? So in terms of acquisition devices, so there are generally two popular ways to do this. One is called the time of flight, right? So we measure the time of light, and then we measure the time. Then essentially the time gives us distance. Okay, gives us a distance. So another way is called structured light, right? We place structured lights and the objects. Then we solve this kind of a correspondence problem to get depths. Okay, so I don't have time to really dive this into details, but you can read the Wikipedia pages, which are highlighted here. But of course, those are ideas, right? How to implement those ideas into physical devices. People over the decades, people have trying to do this, making the device more stable, lightweight, and easy to use, right? So, So back before 2010, so this was primarily done in lab environment, right? So the very big acquisition devices, and we need some clean environment for scanning. I think the game changer is called this Microsoft Kinect, which was introduced by Microsoft back in 2011, and this is really a portable depth sensor devices that a lot of people are using it, right? A lot of applications, but going further, as the depth sensors right now being integrated into mobile devices, right? So I think there are very exciting progress recently on this front. So the depth sensor gives us the so-called point cloud, right? So when you place a depth sensor with respect to the object, what you get is essentially a partial scan, right? A partial surface, recorded as a point cloud. And what we need to do for reconstruction is that we have to align those depth sensors from different depth scans from different views into the same coordinate system. And this is called registration, right? So there are many registration algorithms. They all started from this algorithm called ICP, right? Which started from some initial guesses. The move the scans to align them among their overlapping vision. And to obtain initial pulses, we can also combine ICP with some matching technique, right? So building correspondences between the scans and matching them, okay? So that is the registration. So after registration, what we get is essentially a set of point cloud points. And we want to turn this into a surface, right? Meaning that points are discrete, right? They are essentially samples from some underlying object. And we want to turn this object into a continuous watertight surface. And what we do here is that this is called reconstruction. A lot of people work on this. This is one of the landmark pipeline for reconstruction. What we do here is that we start with some point cloud computer normals. We estimate the sign distance function, right? That is called implicit representation. Then we use a technique called marching cube to turn this into an explicit representation with the triangular mesh, okay? So to recall that, we talked about for 3D reconstruction, there are three steps, right? First, using acquisition devices to get depth scans. The second step is to align them. And the third step is to perform reconstruction, right? To perform reconstruction, okay? And so this kind of reconstruction pipeline have been widely used in different scientific disciplines, right? So trying to develop the more domain-specific acquisition devices and domain-specific restoration and reconstruction techniques. So let me just give you a few examples, right? So this is called Kinect fusion, right? So using the Kinect sensor, and we can do real-time reconstruction by designing suitable registration reconstruction technique. This is one of the landmark results in the field of 3D computer vision and geometry processing. And so this is this is applied to the medical domain, right? So the goal here is that using some so-called this intraoral scanners, very small, right? Introduced very recently, try to reconstruct the human teeth, right? So once we can reconstruct the teeth, so what we can do here is that it enables many applications. For example, we can do implant planning, right? For example, filling the teeth, right? We can do surgery planning in advance, okay? And what we can also do is we can adjust the teeth, right? So this is a very, in fact, this is a very big market right now, right? So we first do the surgery planning physically. We can use 3D printing techniques, I will talk about later, to generate this kind of teeth braces, right? So to rectify your teeth, okay? So this is a very interesting area enabled by 3D reconstruction. I'm working on this as well. And there are many other applications. Let me just give you two more, right? So we can also do this kind of bridge damage inspection, right? So we have a bridge very old, and we want to see how stable it is. What we can do here is that we can use depth sensing techniques to reconstruct those bridges in 3D, and we can do some simulation to analyze the damage, right? So this is also very powerful, okay? And there are many applications in entertainment, right? We are trying to reconstruct digital characters using 3D reconstruction techniques, right? So for example, for movie and games applications. Okay, so the final applications is reconstructing our physical world, right? So in 3D and building a high dimensional map, not just like this kind of two-dimensional map. We want to reconstruct the buildings, like the roads, right? Even like this kind of lanes, like traffic lights, all the static objects, right? So with this map, and this really helps the autonomous vehicles. For example, Google and Waymo are using those kind of technology to help, right? To help the autonomous vehicles to do path planning and navigation and so on. Okay, so this is a really exciting domain. And in particular, with the progress in depth sensors, I think this field will continue to grow. So I have been working on this for many years. Here, I want to basically highlight a few projects that somehow complement what people have been doing. Okay, so the first one is about simultaneous registration and reconstruction. This was a project I did at Google Street View, okay, about 10 years ago. So the motivation here is that in the standard reconstruction pipeline, we have 3 steps, right? We have acquisition, then we have registration, reconstruction. And it turns out that reconstruction and registration tend to be separated, right? So this project was to unify them. So the idea is very simple. Instead of aligning the depth scans between pairs of depth scans, we are aligning the depth scans to a deforming model, right? So so top showed the depth scans, the bottom showed the deforming model, and we update the scan poses. We also refine the deforming model. Okay, so in the end, what we have is that all the scans are aligned, and also we have a reconstruction. Okay, so the benefit of this is that since all the scans are aligned to a deforming model, we can use very sparse and noisy scans. And we can also handle a lot of number of scans, right? Because each scan is only aligned to a particular model, right? So the complexity is linear in the number of scans, okay? So meaning that it's efficient. So in the internship, we applied this to solve the very challenging problem, post estimation problem. Okay, in using the very spot scans attached to a robot. Okay, and at that time, at the very beginning, so my mentors, who is right now is the head of research at Waymo. So he mentioned that I think this was not that possible, right? Just using depths, the scans, we can get this kind of a pulse. Okay, in fact, there are more than 30,000 depth scans, and so. But we did this, and it turns out that what we can do is that we can not only estimate the pulse of the moving robot. In fact, there are many moving people here. Okay, it's very challenging, and we can also reconstruct the underlying environment. For example, the two sides of the panel, right? So those are the aligned. So this is the reconstruction. This is the aligned point cloud, right? So this was the one floor of the Google Earth building. And this, if some of you have visited the Computer History Museum in Mountain View, so this you probably recognize this is the first floor, okay, of the Computer History Museum. So it works remarkably well, and also works for outdoor, okay, works for outdoor, right? So we can use the LiDAR points associated with the autonomous vehicle to estimate the pulse and reconstruct the physical environment. So that is one thing that I want to mention. Another thing that I want to mention is called uncertainties. This might sound it's like a jargon, but I really want to point out the importance of doing this, okay? Not the way how to do this, right? So I want to use the teeth, right? So the teeth reconstruction as an example, right? For example, using an intraoral scanner, we reconstruct the teeth like this. And the question here is that we really want to understand how accurate this reconstruction is, right? Because later we have to do surgery planning, etc. If we don't know whether this is accurate or not, it causes a lot of problems, right? So, but this turns out to be difficult because we don't know the underlying ground truth, right? So we are just, we don't have that, right? So we want to understand whether this is good enough, and where, if not good enough, how to add scans to improve the reconstruction. And so in this year's SIGGRAPH, which is a premier conference for computer graphics, so we introduced a technique that models the noise of the scans, and that so that we can also model how the noise propagates from the input to the output. We can predict the error of the reconstruction. And it turns out that this is somehow consistent. Okay, it's consistent with the reconstruction error. Okay, so I think this is very important for 3D reconstruction. So my lab has been doing this and will be doing this for the next few years. Okay, so far we have talked about the standard reconstruction pipeline, right? So that requires very dense input. But if we think about for mobile applications, right? So using a cell phone, it's not really affordable to store all the depth sensors captured, right? That requires a lot of memory, a lot of computation power. And motivated by the fact that now we have a lot of data, the ground question here we want to ask is that, can we actually reduce the number of scans? For example, the scans just cover the surface, right? Instead of duplicating the surface many times, right? So using some data prior, okay? So the critical question here is how to estimate the pulse, right? Because for the registration, we require that the scans, right, to overlap, so that we have they have overlapping vision, or we can extract features to match them, right? So, but the question here in the field view case, right, trying to reduce the number of scans, is that, can we do this for scans that barely overlap or no overlapping, right? Can we do that? But it turns out that if we think about how humans do this, right? So for example, if we want to scan the human body, how many scans we need? Pretty much we just need 2 scans, right? One is the front, the other is the back, right? So if we have that, because we have essentially a lot of priors in terms of the human model, we can leverage this prior to put them together, right? So for the reconstruction, okay? So this really motivates us. What we can do here is that we can use the so-called scan completion. So this is the paper published last year at CVPR, and Jeffrey was one of the authors. So what we did here is that we are trying to use the machine learning techniques, AI, machine learning, artificial intelligence techniques, So given the scans, we are trying to extrapolate, right, to predict what the surrounding area, to enlarge that, right? For example, for the case of humans, given the front, we want to predict the back, the back, right? Pretty much we have a good knowledge of that, okay? And we want to do this for general objects, right? So we apply machine learning techniques to learn how to complete. And once we can do the completion, we can solve the registration problem. Okay, so that is the idea, right? So I just want to show you some of the results, right? So we have this kind of ground truth, and our approach can predict the relative poses even of two scans, even they do not overlap. Okay. Okay, and this works remarkably well. The third row is our technique. The other rows are the baselines. Okay, so in all the other cases, right? So like non-overlapping scans, like small overlapping scans. So our approach works reasonably well. Okay, and using this enables field view reconstruction, right? So for example, for endorsing 3 or 5 scans are sufficient, okay, for reconstruction compared to with using hundreds of scans. Okay. Okay, so that is the end of the first part of reconstruction. I think this really move from this kind of traditional dense reconstruction from right now in the AI era field reconstruction, and in fact a lot of research have been focused on single view reconstruction. Okay, so I did not have time to mention that. Okay, so now we have the 3D models, right, in computers. Then I want to move to the second part of the talk, which is the most interesting part, called processing analysis. So I will focus on analysis, which is most relevant to artificial intelligence. Okay, so the goal here is try to really understand 3D geometry. Okay, really understand 3D geometry. But this is a very fuzzy word, right? Understand, right? So in fact, that this field is defined by a few important like the core tasks, right? So those core tasks characterized in terms of the scale, right? We have this kind of local analysis, for example, curvature. We have this to estimate the curvature of the 3D model. We want to do symmetry detection, right? So there are a lot of symmetries in, like, for example, windows are line on a row, right? So for example, most object reflection of symmetry with each other, right? So this is a task. And there are also like semantic tasks like segmentation and part detection, right? We want to segment the object into parts, okay? And we want to not understand a single object, we want to understand how objects are related to each other. That is called matching. And we also want to do this kind of more general task like retrieval, classification, clustering, and those tasks involve a collection of objects. Okay, so those are really the primitive, the tasks for 3D understanding. So for in terms of applications, we usually combine those tasks, right, techniques to form a complete system. So let me just give you one example, which I worked on a couple of years back. Right, so the idea, the goal here is to resemble fractured surfaces. Remember, imagine that you have object, you broke it into pieces, right? So very much related to the first project I mentioned, but we want to develop a computational solution to this. So what we do here is that for each fragment, it has this kind of surfaces of these fractured surfaces, and also the regions that belong to the original object, right? So the first step here, we want to do segmentation, and we want to do feature extraction, understanding for example, the features in the fractured regions. Given that, we can do this pairwise matching, right? So we can match pairs of fragments, and then using the pairwise fragments, we want to do multi-piece matching, right? So pretty much you can see that we have to assemble a lot of tasks here. So this is basically just one applications of shape analysis, right? So for example, in oral domain, right? So we can segment individual teeth, right? So that is important for surgery planning as well. Okay. Right now, shape analysis or in general geometry understanding is a very popular area, because now we have a big data, right? The emergence of big 3D data. In fact, that very recently we really have more and more 3D data now, right? So instead of a single object, we have collections of objects, right? So there are a lot of internet modern repositories for this, right? 3D warehouse, UB3D, Princeton shape benchmark, Redwood, right? So we are not just having repositories for 3D models, we also have repositories for 3D scenes, like this kind of indoor scenes, outdoors, etc. Right? So that really provides a foundation for developing machine learning techniques for geometry understanding. So I want to mention two projects that I'm involved. One is ShapeNet, which is one of the default data set for evaluating shape understanding tasks. Okay. And another, so this is for general shape categories. A very recent project we focus on mechanical parts, right? So the applications is trying to understand, for example, the for help factories, right? So to install AI machine learning techniques to speed up the production pipeline. Okay. So here I want to mention what the question had, for example, in the image domain, in other domains, we also have big data, right? We also have big data, right? So for example, in images, we have ImageNet, right? For understanding images, we also have data sets for understanding videos. And what is really the difference between this kind of 3D domain, right? Geometry processing and the image domain. So one thing I want to mention is the notion of representation in machine learning, right? So if you think about, for example, the task of we have a point cloud here and we want to detect the objects in this point cloud, right? So that is a task. But it really has a gap between this and the standard notion of machine learning, because machine learning, for example, it's dictated by X and Y, both are vectors, right? So X is input, Y is output. Both of them are stored into vectors. So there's really a gap between this kind of notion called the 3D understanding, right, the geometry objects, and the standard notion of machine learning techniques, right? Okay, so what does that mean is that we need to think about how to represent 3D models, okay, into vectorized forms to apply machine learning techniques. And I think this is a critical question in this domain, right? If we think about the 3D model, unlike images that usually stored in the regular grid, as 3D models have different ways to encode, right? For example, we can encode this as a volumetric grid or implicit surface, right? For example, circle x squared plus y squared plus z squared minus 1. That is an implicit function, okay? But we can also encode this as a triangular mesh, right? For example, it's basically a collection of faces that stitched together in a continuous surface. And we can also represent this as a point cloud, right? So this is what come out of the scanning acquisition devices. So we can also represent this as a parametric surfaces, right? So by performing parameterization, right? So the interplay, the conversions among those representations, that is called geometry processing, right? So remeshing parameterization. And I don't have time to dive into details. Okay, but above that, we also have this other representations like constructive solid geometry, right? Multi-view representations, scene graphs, right? Semantic segments, right? So there are different ways to encode the 3D data. Okay, as a central question here is what is really the right representation to encode 3D geometry for performing geometry understanding. Okay, for performing geometry understanding. And I think this is a very open problem that has not been solved so far, okay, in this domain. But besides like encoding data, we also have the notion called output representations. For example, if we want to detect objects, right, so objects encoded the bounding boxes, there are also many ways to encode the bounding box, right? For example, so may I ask you like how to encode like a cube in 3D? Like any of you have idea? How many parameters we have for a cube in 3D? right? So one way to encode, that give you a hint, is that we have a center, right? Then we need to determine the orientation, right? So that is the 1 degree of freedom, right? 2 degrees, or the 3 degrees of freedom, the orientation of the box. Then we have basically the scalar in each direction, right? So we have 9 parameters, right? If we assume that the box is around it's always under the ground, then it reduces 7 parameters, right? So there are different ways to encode the bounding box, right? So those are also called geometrical representation, right? So that is related to how we relates how we represent the output in a machine learning algorithm. Okay, so recently we introduced the notion called the hybrid representation, right? Not just using one representation, we are using multiple representations to encode the bounding boxes, and then aggregate the prediction together. We can get significant performance gains than different other encodings. Okay, so my message here is that thinking about in the 3D understanding, thinking about how to encode the input and how to encode the output into vectorized forms, this is the fundamental problem. Okay, and it affects the performance a lot, right? So we apply this to do 3D object detection, right? So given a 3D point cloud reconstruction, and we want to understand what are the objects in the scene, right? So we can do reasonably well. In fact, we can also apply this to sports point cloud, and this connects to the autonomous driving setting, right? So for example, the autonomous vehicles, they have LiDAR sensors, and the LiDAR sensors produce such a point cloud, okay, for 3D understanding, okay? Okay, so this is a very, very broad field, right? So it's related to machine learning, in particular supervised learning, right? We require label data to train such kind of systems. A very interesting question is that now we have 3D data, but can we ignore the neighbors, because the neighbors are very hard to obtain, right? So this, I call it unsupervised analysis. I will have two very interesting stories here. And in fact, this is a very interesting field, and the output can be also used to train your networks, right? So it really connects to deep learning. So let me walk you through 2 examples of why this is interesting and possible. Okay. So again, we still use the assembling the fracture pieces as an example, right? So we have 2 pieces here. Because we don't have sufficient features, right? So even for humans, right, how to assemble them is challenging, right? So in fact, that there are many ways to assemble them, right? So you actually don't know how to do it, right? So there are many possible ways. Okay, many possible ways. Right, so I believe many of you have done this, right? The solving puzzles, right, in your life. Okay, so in this case, what would you do?
Is it something related to like reinforcement learning, like try out various combinations and have some kind of like a score or something?
It's not, reinforcement learning is an interesting idea. Okay, it's an interesting idea. But here I want to talk a little bit about another message here. Okay. Right. So what we do here is that we are not just looking at the 2 pieces, right? So we shall look at another piece, right? For example, in this case, is there? Okay, we should again. Okay, so here what we do is that instead of looking at 2 pieces, we are looking at another piece. Okay, it turns out the 3rd piece and the 1st piece has a very strong texture match, and then we know that this is a very good match, right? But we are utilizing not just the information from 2 pieces, we are utilizing information from all 3 pieces, right, together. So this really shows that, right, leveraging data, we can do things a lot better. Okay, if you don't understand this, let me give you another example. Okay, say we have 2 3D models, and we want to build correspondences between them to transfer even geometry information like textures from one model to the other. So in this case, what we do is that we go to the internet, we download some 3D software, right? So we press a button, we feed those two models as input, press a button, then we give some output correspondences. But because those 3D models are slightly different, and does not really give you the clean correspondences, right? So there's some bad correspondences that are colored in red here. So in this case, what do you do, right? So what do you do here? To improve the algorithm, right? So, but that is difficult, right? You may not understand the algorithm and the paper, right? So you may not even understand the hyperparameters. But in this case, I can tell you that using data, there's a very simple solution, okay? Very simple solution, right? So instead of improving the algorithm, you just find another intermediate object, right? So that the shape sits in between those two models, and then use the same software without changing the parameters, right? You just load the models, press a button, boom, right? It gives us, in this case, because the shapes are similar, okay? It gives you two good maps, right? Now what do you do? Then you can compose them to obtain a much better map between the first original two objects.
Oh, is this related to that idea of like autoencoders or something, like when you have like an intermediate encoded thing and then you decode it to another form?
This is not related to that. This is related to this the idea called the big data, nearest neighbors. Okay. Okay. So in fact, I have one slide about autoencoder later. Okay. Okay, so this is another example where leveraging data we can improve the maps, right? But of course, to turn this into algorithms, we have to do something slightly different. So we can think about a collection of objects, right? So we have this kind of maps between pairs of objects, right? So the argument is that some of the maps are bad, okay, because the shapes are different. But I want to argue that the network approximately correct maps is still a connected graph, right? Because if it's not the case, you can throw in more shapes so that each shape is surrounded by some similar shapes, right? The same algorithm, you don't know the algorithm, but the same software outputs good maps, okay? So with this, we can introduce so-called map synchronization problem where given a graph of maps, and we want to identify the good maps. Okay. So this is called map synchronization problem, and we need a constraint, right? Otherwise we cannot do this. It turns out that there's a very natural constraint called this kind of consistency, right? Meaning that if we have maps you compose along a cycle, right? For example, 3 objects, right? We force a cycle. They should be consistent, right? So they should go back, right? When you starting from a point, apply to the point on the second object, the third object, and back. This should be identical, okay, to the identity, okay. And it turns out that this is inconsistent. This is consistent, okay. So I have a bunch of work that using this kind of consistency constraint to rectify the maps, okay, among collection of objects. And this is also relevant in the deep learning era, because in the deep learning era, you can think about also build a graph where nodes representations and edges neural networks, right? So we can use those kind of consistency constraints to do network training. And those are some of the recent works on this. Okay, so far this is about the correspondences and matching. And then what about segmentation? It turns out the segmentation, we can do something very similar, okay? So let me ask you this question, right? So for example, so why chair's back is apart, right? If you look at a single object here, it's very hard to tell, right, which is apart. Suppose you have never seen a chair before, right? So it's very, very difficult to say that the back is apart. But let me ask this, right? Using data, we have the data has some variation, right? So for example, if we see a stool here, then you know that the back is added to the stool, right? So then in this case, you can say that the back is apart. But of course, to turn this into algorithms, we have to compute the related objects, computing correspondences, and understand the variations. Okay. For example, this can be helpful to rectify over segmentations. right? So for example, the chair legs has weak connections, you tend to cut. But if we enforce that all the glass models had the segmentations should be similar, then you want to be able, you want segment here, okay? And we can also rectify under segmentations, right? Because all the models the segmentations should be structurally similar. So all those techniques are enabled by data, and we are enforcing some generic constraints among them. So recently we have serious works that turn this, I call this variability driven segmentation understanding, right? So we don't have labels, but if we given the data, we can still understand the 3D models, okay? And I think a very interesting question is how to combine this with deep neural networks, okay, autoencoders, okay? So that is a very interesting thing to study, okay? And the advantage of doing this is that we don't need labels, okay? In fact, label those part segmentations are very tedious. Is very tedious. So what after shape segmentation, shape understanding, what are the applications, right? So once I understand this, right? I showed one application of assembling fractured surfaces. That is one application. Other applications include geometry modeling and synthesis, right? For example, this is a very famous work called modeling by example, right? It's also enabled by having data, having segmented 3D models, right? So we can combine different parts of different models to generate new models, right? So that is the way, right? A very interesting idea for design, right? We do not need to draw each new models from scratch, right? Design each or reconstruct each model from scratch. We can leverage what have been models so far, right? We just combine them to form new models, right? So following this work, there are many follow-up works, right? So doing synthesis using different techniques. And recently, people have been doing this using neural networks, right? The generative 3D model, right? So most of the works have been focused on images, but there are recent works that try to generate 3D models using deep neural networks, okay? Right, so for if you're interested in this, right, so I have caused two state-of-the-art reports on this. Okay, so I want to talk a little bit about one work that I did with my student and colleagues at UT and industry companies. So we did a work that using deep neural networks to generate 3D scenes, right, indoor scenes. So what we do here is that it's again, right, so it's related to how we encode the scene, right? So it's basically what is the right vectorized representations for 3D scenes. And we introduced a matrix representation, right? So that the element encodes whether object exists, the location, size, orientation, and some shape descriptors. We train a generative model to synthesize 3D scenes, right? So we can synthesize a diverse set of scenes, right? So there are multiple objects in the scene, right? So we can do this for different types of rooms. Right, so that enables applications such as scene interpolation, right? So given a completion, right? So given some objects, we can add more objects to it, right? So that to produce semantic meaningful results, okay? Like different cabinets, like tables, right? The monitors and so on, okay? And we can also do so-called scene interpolation, right? The given two scenes, right? So we want to find what are the scenes in the middle, right? So smoothly interpolate, right? So this is also a very interesting application, right? We can find the plausible scenes. Okay, so those are enabled by the very beginning by understanding, right? So for example, segmenting the scenes into individual objects. After that, we can train models to generate new scenes. Okay. Okay, so that is about analysis. I think this is a very interesting active research area with many applications in biology, in medicine, in the dental domain, right? So the last part I want to, right, so for example, one application is modeling and synthesis, generating new 3D models. And in the last part, I want to talk about the 3D printing, right? Once we have 3D models generated, we can actually use 3D printing devices to generate new models, okay? So what is printing, right? From Wikipedia, printing is a process for reproducing text and images typically with ink and paper using a print press. Okay. 3D printing essentially is the 3D process printing, right? So 3D printing is the process of making a real physical 3D object from digital file using some material in a manner similar to printing images on paper. Okay. Right, so the basic, how to do 3D printing, the basic idea is to slice the objects into layers, making the object layer by layer. Okay, so that, right, so this is right, so very simple idea. Okay, so if you have never seen a 3D printing before, I can't believe you. Okay, because right, every of you have seen this before. Right, this is a 3D printer. Okay, ice cream. Right, so what you do is that, right, you have this kind of stuff from the beginning. Right, so you can, right, it's additive procedure. Right, so this is a 3D printer. Okay, so the process of 3D printing has this kind of a differential. Right, slice the object into thin layers, then integrate the built layers with ink and glue them together. Okay, so this is the procedure, right? Example of 3D printer, right? So you have this kind of working volume, right? So it prints layer by layer. And layer by layer, okay? So eventually, after a few minutes, what you get, you will get something like this, right? Something like this, okay? So this allows you to print arbitrary shapes you want, okay? Arbitrary shapes you want, okay? And the different types of printers, right? So the big ones, like this kind of the last one, I think is quite affordable, about $100, okay? In fact, the printing material is probably more expensive, right? So than the printer itself, okay? 3D printing has many applications. In fact, the many critical ones, okay, vital ones, right? So industrial design, it really allows you to design specific object, right? So, and very fast manner, okay, very fast manner, right? So fashion design, decorations, right? In fact, printing food, right? So this is right, it's a different kind of food, okay? 3D printing technique, okay? And medical treatment, okay? If you go to Google search this 3D printing medical, you can find a wonderful story. So it really is saving a lot of lives, right? Printing this kind of like the small objects for surgery, okay? And very fast manner, okay? Within like 1 hour, okay? So there are a lot of wonderful stories, right? You can also print teeth, right? So doing implanting. So this is a very important application area. And right, so right, architecture, right, is another application of 3D printing. So in terms of research, so there are many research related to 3D printing, mostly related to physics, right? Because we try to design physical objects, and we want the physical objects to have some special properties, right? For example, like we're trying to make it stable, making it stand, right? So that the printed object is very rigid, robust, right? So if the object is very big, how to decompose the object into parts and print the parts and assemble them together, right? So I'm printing not just like this static object, printing this kind of articulated object so that it can be deformed, right? The spinnable objects. So I want to mention 2 works that I have done, and this is mostly done with collaborators. So basically, I'm a message passer, okay? So the first work is really thinking about the full pipe, the total package, right? So if we want to print a large object, right? So that entire object does not fit into the printing volume I showed in the video, right? So in this case, we have to decompose this into parts, but not about that, right? We also want to pack the parts in the printing volume, right? Because the printing speed is not that good, right? So we really want to really lower, right? Pack them together. So this is called a decomposition assembly. So in this work, we try to find the algorithm using the search in artificial intelligence and optimization, right? So to really optimize the decomposition and assembly, right? So we trying to to reduce the height of the printing, the packed objects. So to reduce the, so first making sure that it fits into the printing volume, and also pack them together. Okay, so this is one of the work. Okay, so I did with collaborators a couple of years back. So there's another work that, right, so this is the result, physical one, okay? So there's another work that really like, is called connected Fermat spirals. So this one, the previous one tried to solve the problem of the printing volume, and this try to solve the speed of the 3D printing, right? So the standard way of 3D printing is called this zigzag, right? So basically the challenge here is that when you do zigzag, when you turn, and it becomes very slow, okay? And also the surface is not that smooth, okay? It's not the outer surface is not that smooth. So in this work, we try to change how the way a layer should be print, okay? Should be print. So the idea here is to use the called Fermat spirals, right? So this is basically equidistant space filling curves, right? Filling this kind of working space. And the emphasis here is that we want to have low curvature paths, okay? In the sense that basically this to speed up the 3D printing, okay? So let me just show two videos here.
3D printing 400 years ago. 1636, Fermat studied an unconventional type of spirals. That Fermat spirals possess compelling properties to make them desirable as fill patterns for 3D printing. A complex 2D layer can be filled with connected Fermat spirals continuously and with less sharp turns than Hilbert curves.
Okay, so this is a real one. So this is the first with the simulation. Okay, let me show you the real one. All right, so this is the real printing. Right, so this is the final one, okay? So you may want to ask, what besides speed, what is the key advantage of this, right? So this figure really shows that, right? So the top is basically using this connected Fermat spirals, right? Because it's smooth. Then you look at the surface boundary here, right? It's quite smooth, okay? But if we use the, right, so this is the default, right? If you purchase a 3D printer, this is how it should be done, okay? And then you look at here, right? It's not smooth, right? Because you can really see the layers, okay? You really see the layers, okay? So that is really the difference, okay? Okay, so there are many wonderful things to be done in the 3D printing domain, in particular applying artificial intelligence techniques, right? To design to automate the procedure of 3D printing. In fact, the very exciting recent works are using reinforcement learning to solve the packing problem. Okay. Okay, so I have a few concluding remarks. Right, so I think if you look at what really what is happening right now, very exciting domain, the deep learning, artificial intelligence, right? So in my talk, I mentioned a few applications of deep learning. I did not go into the details of network design. Okay, that is from my perspective not that interesting. But at the big picture, right, we have deep learning, we have artificial intelligence. The driver for those, right, the two factors, right? One is data, right? We have a lot of data now, both labeled and unlabeled. We have hardware advances, right, so that we can train deep neural networks in a reasonable amount of time. And I think that in the 3D domain, this is very exciting because the 3D data continues to increase the scale and diversity. And I think we'll have more and more data enabling us to solve more challenging applications. And I also want to say that from the science perspective, right? So 3D data has, as I mentioned, this is still open problem, how to represent 3D data into vectorized forms. The computer graphics community has not solved this, right? So, and I think this is a fundamental challenging in artificial intelligence, right? So deep learning era, okay? I think what I want to say is that we are just getting started, right? So there are many interesting things to do, okay? So I want to end my presentation here, and I'm happy to answer questions.
I have a question about that ferment spiral thing. Is the spiral which is like constructed always identical? Like, is the answer always the same?
So it's close to be equidistant, okay? Close to be, right? We solve optimization problem to making sure that the distance between adjacent this kind of curves, right, spirals, is the same. Okay.
Okay.
Yeah, I don't see any questions on Slido right now. So if anyone has any, either feel free to ask there or in fact, just ask over Zoom. Also, on another note, thank you all for tuning in today, and we'd love to hear your feedback for on this talk, and also so we can improve our future talks. So I just sent a link in the chat. If you want, please fill out the feedback survey. We'd really appreciate it. All right. Any questions?
Right, so I showed many applications. If you are interested in those applications, I'm happy to answer.
Okay. Hey, this is Ruben. Can you hear me?
Question.
Yeah.
For your dental data set, like for the dental work that you are doing, are your data sets publicly available, or?
So I'm primarily working on the reconstruction, and that does not really utilize any private data. It's basically a 3D reconstruction technique. And for the later applications of implanting, yeah, so that data is not yet available. Okay, so we have to go through a legal procedure to release it. Okay, so I should say the medical data piracy, okay, is a very important. In fact, in particular for 3D geometry processing, I think privacy is an important aspect. Okay, not explored very well. Okay.
Okay, thank you. Yeah, I was just wondering whether the thing is publicly available, like whether there was a data set for it. Oh, cool.
Yeah, I think the medical domain, the data piracy, in fact, most of the data sets are not that big. Okay, I think this kind of, this is also a fundamental challenge of the, to develop efficient machine learning AI, artificial AI technique. Okay.
And I believe Ruben had a question.
Oh yeah, I heard you mention the registration.
Yeah.
In the medical imaging domain, we have rigid and non-rigid registration. Well, what you mentioned basically is a rigid. Okay,
rigid.
great, great.
Yeah, so I can mention, I did not mention non-rigid registration. So I personally have a paper, a couple of papers on that. So I think a non-rigid registration has similar, it's more challenging, right? Because the the number of variables is significantly bigger. But it has the similar issues with widget, right? So uncertainty, for example, is something that very important for non-widget ones, right? So and in particular in the medical domain, another issue is how to do this from a few, right? So if you are doing reconstruction, how to do reconstruction from a few observations, that is also challenging, right? So non-registration, the challenge is how to model the underlying deformation, right? Because you don't know that.
Yeah. But a lot of projects, for example, in the cardiac, the dynamic.
So that is also related to, for example, like building correspondences, right? So in analysis, how to build correspondences across objects, right? So for the idea of using, for example, we are aligning, matching two deforming objects, if the deformation is very big. So the second part of the talk, I talked about idea of using intermediate objects, right? So you're not just aligning two objects on the big deformation. You want to insert intermediate objects, matching between similar objects, then compose the deformations.
That's always true. For example, in the cardiac procedure, depending on the heart rate, right? Yeah. If the heartbeat for the neonatal is pretty fast, that's more challenging. Yeah. Okay, great. Thanks. Yeah.
I have a question.
Go ahead.
For your Draper research, when you're printing the pieces on top of each other, wouldn't they stick together?
You mean 3D printing, right?
Yes.
So that is basically is pretty much automatically assumed, right? Because the basically depends on the material, right? When you do the printing, right? So it's heated up, it becomes more fluid, right? So when you print it layer by layer, the material tend to stitch with each other together.
Yeah, but you wouldn't want that, right? Like for your Draper project, because later you'd have to.
So that one, what we can do here is that we can add some additional separation, okay, separation between the objects.
Like support.
Support, for example, right? Later we call the support.
Oh, okay, I see.
Yeah. Very good question. Very good observation. So what is the difference between registration and reconstruction? So registration is trying to align the scans, right? Putting them together in a point into one point cloud. Reconstruction is turn that point cloud into a mesh, into a surface. Okay.
But as one example, CT reconstruction is totally different, right? Yeah. What you talk about is optical reconstruction. That's really. I have another quick question. The first slide you mentioned, there's in the 3D vision, you include the structured light model, right?
Structured light is a depth type of it's a category of depth sensors, right? So what we have here is that, for example, in 3D vision, if we take two images of the same underlying environment, if we can establish very accurate correspondences between the images, then we get depth. We can turn the RGB, right, to the images into 3D depth scans. So that is the principle of the structured light. But what structured light does is try to project lighting patterns on the surface so that the correspondence computation becomes a lot easier.
Yeah.
That is a structured light.
Yeah. But from your chart, my understanding, actually my first project in college is we only need one camera and one projector, right?
Yeah.
Project maybe spatial coded structure light on the surface, and then use a camera to measure the 3D information, right? But your chart is.
that is different, right? So in terms of structure line, we still, in principle, we need 2 images, right? We need 2 images.
I agree. Yes.
In principle, we need 2 images. And if we can project the light, right? If we have one camera, we can move the camera. We need 2 images, right? How many cameras we need? It depends on the setup.
Yeah, but
images. How many cameras we need, depending on how you produce those 2 images.
Yeah, usually for 3D vision, we need at least 2 cameras. Yeah, that is conventional. But for structured light architecture, if you project a special coding pattern onto the surface, and then use a camera image to decode the position, actually you can solve a matrix to solve the corresponding 3D.
That is also possible. That is also possible.
Yeah. It was feasible. That's why it was my
that is
college project. Yes, especially in the medical application, you can measure a lot of, for example, artificial shapes. Yeah. Okay. Great. Thanks.
All right. Any other questions? If not, then thank you, everyone. Thank you, Professor Huang, for your time, and everyone have a good evening.
Okay, thank you. You can email me if you have additional questions. Bye. Okay, on my webpage. Okay, thank you. Okay.